Right, here we go with the second bit of 5.4. Okay, we were graphing these trig functions, basic trig functions. We looked at sine and cosine, which are nice, what we call sinusoidal in the sense that they have this sine wave, right? So quickly, if we have a look, if this is our original 0, we're going to go up to 1 and down to 1, because if you think about a unit circle as we go around, right, we increase up to 1, then we go down to -1. So if you look at a cycle being 4 quadrants, this would be pi over 2 then. You know what, I don't have to write all those things because it gets kind of confuses it. How about if I put pi and 2 pi and then 3 pi and then 4 pi? Okay, so if you think about a cos function or a sine function, sorry, y equals sine theta. Okay, you start in the middle, you go up to the top in the first quarter, middle second quarter, bottom third quarter, back in the middle by the fourth quarter, and you end up having this periodic function, this cyclic function called a sine wave. Okay, so sine, if you remember that sine 0 is 0, you know that you start here. If we look at y equals cos theta, all right, it still goes up to 1 and down to -1. It starts at 1, however, because cos 0 is 1. If we break it down into those 4 quadrants again, this being pi, that being 2 pi, so that's pi over 2. Every quarter, it does part of its rotation. So you just down, up, boom, middle, down, up, boom. And if you follow these patterns, then it ends up being relatively easy to graph, okay? Now the sine, or the tan function is a little bit different. If you remember in a unit circle, right, sine theta is equal to the y value here, cos, right? Cos theta is equal to the x value. Remember the unit circle, okay? Quickly, the unit circle is this, where it's got a radius of 1, so this is 1, 0, this is 0, 1, this is -1, 0, this is 0, -1, right? So as you rotate around, sine is 0, sine is 1, sine is 0, sine is -1, sine is 0. Cos is 1, right? Cos is 0, cos is -1, cos is 0, cos is 1. And that's how we transcribe those values onto an xy axis. That xy axis being a little bit longer in this way, it does obviously go back the other way as well. We're looking mostly at the positive one right now, okay? So what we're going to look at quickly here is just graphing tan theta. It's a little bit different. Notice that for your sine and for your cosine function, your period is equal to 2 pi. And here, your period is equal to 2 pi. We measure the period from the time it takes or the distance it takes to do one full revolution. Please realize that just because you're back at 0 does not mean you've done a full revolution. You still got to do the bottom bit. So often it's easier or more practical to read from the peak to the peak, trough to the trough, or looking at the whole cycle. Peak to peak, trough to trough, okay? Peak to peak, trough to trough. When you're looking at graphs, sometimes you're going to look at the peak, sometimes you're going to look at the trough, sometimes you're going to look at the middle to find the period, because not only is the period equal to 2 pi, right, your b value is equal to 2 pi over your period, and your period is equal to 2 pi over b. So there's ways to find the b value for your equation. Remember, your equation looks like this. Y is equal to a, let's say sine b of x minus c plus d. So this b value, remember we looked, b value changes the period, so it shrinks it or increases. It's a horizontal stretch, right? A changes your amplitude, C has your phase shift sideways, and D is what they call your vertical displacement. A quick review of the previous section before I jump into tan theta, okay? Now, first of all, remember that tan theta in your unit circle is y over x, or, yeah, so the opposite over the adjacent. X obviously can't be 0. If x is 0, then you have what we call a restriction. And restrictions, you know, manifest themselves on graphs as asymptotes. So what happens here is that x equals 0 at 90 degrees and at 270, right? At 90, at 270, if you think about a unit circle, right? If you have tan theta equals y over x, right? This is 1, 0, no, this is 0, 1, and this is 0, -1. When x is 0 at 90 and 270, or pi over 2 and 3 pi over 2. Okay, so that means that those are what we call asymptotes. So what you end up with is a graph that looks like this, okay? Negative pi over 2, every pi over 2, or at pi over 2, and then every pi after, right? Every pi is half a rotation. So at pi over 2, and then 180, 180, 180, 180, pi, 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 pi. So every pi, you have another asymptote. Now, what that really is important to remember here is that your period is pi, not 2 pi, like it is for your sine and cosine functions, okay? Now, let's think about what happens with the tan function, right? We don't necessarily know what the tan function, well, hold on. So if you have a 45-degree angle, this is the one where the tan function, the opposite over the adjacent, okay, would be 1 over 1. So at 45 degrees, which is halfway between 90 degrees, you have 1. And then you have a negative 1 here. And then, okay, it's 0, right? Y is 0 at 0. So if y is 0, you have tan theta is 0. So 0 at 0, and then at pi, and every pi again, and then it's 1 there, and it's negative 1 there, and it's 1 there, and it's negative 1 there. And what you end up having, if you try something like tan 89, I wish I had my calculator with me right now, but try tan 89. Try tan 89.9. Try tan 89.9999. And what you'll notice is that this value just keeps getting huger and huger and huger. It basically approaches infinity, and we end up having a graph that looks something like this. And if you don't believe me, you can graph it on your calculators. I apologize, I don't have my calculator ready to go right now, but this is essentially what you're looking at when you're talking about a tan function, okay? Now, remember that if we had a period of 2 pi, it was 2 pi over b, and then your b was 2 pi over your period. Well, in this case, because my period is tan, for tan is pi, all right, then to find the period, you go pi over b, and to find the b, you go pi over the period instead of 2 pi. Okay, now the b value is for our equations, and the period is for the graph. Now let's quickly look at the domain and the range. The range, you can see, goes forever up and forever down. So we're going to say the range, the y values are an element of all real numbers. The domain, however, is restricted by the asymptotes. So x cannot be pi over 2. Okay, it can't be pi over 2. And it can't be every pi after that or pi before that. So what we do is we write a general description like this. We go x can't be, pi over 2 or pi plus pi n. N being an integer, okay, a positive or a negative number. So we can have a clarification. N is an element of an integer here, okay, to indicate that it's every pi. So plus pi plus negative pi plus 2 pi negative 2 pi, however you want to sort that out. That is essentially all I wanted to show you about tan functions. Maybe I could have thrown it into the other section, but I thought doing it separately on its own might not be a bad idea. I'm going to try and put another video up maybe to show you how to graph some of these functions. Yeah, so there we go. Try some of the sections, try some of the questions. Graphing them will only happen if you keep trying a bunch of them. It becomes quite a pattern, and it's quite predictable. If you can get out of this equation, if you can get those 4 values, do not forget that the transformations work exactly like they do for all the other functions that we've looked at, okay? Vertical stretch, horizontal stretch, horizontal displacement, or phase shift, we call it in this case, and this is a vertical displacement, right? So the same thing, if this looks like x minus pi over 2, that goes right pi over 2. These transformations apply also to the tan function. They're a little bit trickier to do. Not quite sure how many of those we're going to get into, but as long as you can understand that those things still work exactly the same way.